All right, let's take a look at these reactions. So in this case, these are going to be aldol addition reactions. So we start off with a carbonyl. In this case, usually an aldehyde, but ketones work as well. We add some sodium hydroxide. And of course, these are at equilibrium, but we have techniques and ways to push the equilibrium towards the product side. And then what we form is an aldol. In this case, an aldol is just basically the combination of the words aldehyde and alcohol, right? Aldol. And then if we think about what these are, we have our carbonyl. And then, of course, this is the alpha position. This is the beta position. So these are oftentimes called beta hydroxy aldehydes. Or if it was a ketone, beta hydroxy ketone, right? And again, aldol just means alcohol plus aldehyde. Think about the mechanism of this. So we have our aldehyde in this case, and we have that alpha carbon, and then that alpha carbon has protons on it, which are slightly acidic. And so we have a base come in and do our deprotonation to form our enolate. And in this case, we have the enolate formed, and then we also have some unreacted aldehyde that's the starting material, right? And so basically what's going to happen is this guy is going to kick back down and then attack our other aldehyde, right? So on the left side, we have the nucleophile. On the right side, we have the electrophile, but they came from the same molecule. And then if we count our carbons, it's carbon number 1, carbon number 2, carbon number 3, and then carbon number 4. And you think about the bonds that are formed, it was between carbon number 2 and carbon number 3. And then after that, there is a proton transfer step to reprotonate this oxygen that would be negative. We're just going to draw it as OH because there's a proton transfer that occurs. And then this is your final product. And of course, carbons 1, 2, 3, and 4, count them out and make sure you understand where they're all coming from. And again, this proton came from the proton transfer step. Let's take a look at another example. Right now, in this case, we have this aldehyde with this benzene ring. Going to react this with some sodium hydroxide. And again, for these kinds of problems, I would either write out the mechanism or just kind of think through it logically. In this case, I'm going to draw out the mechanism. So that's our acidic proton that we're going to lose with our hydroxide to form our enolate. So on one side, we're going to have our enolate. And then we're going to have some leftover aldehyde that's in the equilibrium and that has yet to be reacted. And then it's going to do a reaction with itself, essentially, right? We're going to do this enolate attack with itself, essentially. And it's carbon number 1, 2, 3, carbon number 4, 5, and 6. And then you can see the bonds that are formed are between carbon number 2 and carbon number 4. And then, of course, we have a proton transfer step to reprotonate the O- that would be formed right there. And then you can go ahead and draw out your product. Right, this would be carbon number 1, 2, and 3, right? That's just from our starting material. You can see that the carbonyl is reformed. And then coming off of carbon number 2, we have carbon number 4, which now has the O-, which gets protonated into an OH. So that's carbon number 4. And then carbon number 4 also has carbon number 5 attached to it. And then carbon number 5 has carbon number 6 attached to it, which is a benzene ring. Boom. And so that's how you would draw the end product. Again, this is a beta hydroxy aldehyde. That's another way that you can think about it. If you think about the alpha position, in the beta position, there should be an alcohol. In this case, if you did this reaction in real life, it actually wouldn't stop here. Another reaction would occur and you'd actually get a different product. So sometimes you can isolate the beta hydroxy carbonyl. Other times it will react further. And we'll learn about that in this next section. In terms of ketones, right, we saw it do it with aldehydes. Ketones can also do this. So beta hydroxy ketones, they can form, but they're not favored. So they're still there and they can do further reactions, but they're generally not favored. So for example, if you had cyclohexanone and then you reacted that with sodium hydroxide, you would indeed get some aldol addition. Again, beta hydroxy there, but in this case, it would not favor the product. The reactants would be favored. And of course, this is at equilibrium, so we can do an aldol addition. We could do a retro aldol as well. Think about the mechanism there. You'll be asked for one of them in the work along.